Welcome back, my dear students. In this video, we will be discussing about the dual space of the classic LP space. So the result is the dual of the LP space is the LQ space where P is a finite number which is in between 1 and infinity and Q is the conjugate of P. That is 1 by P plus 1 by Q should be equal to 1. So we are going to prove that the dual of LP is actually the LQ space, which means we have to have an isomorphism from LP dash onto LQ. This function should be bijective, linear, and preserves norm. Before getting into much details, let's recall what is an LP space and LQ space. The LP space or LQ space consists of sequences such that summation j is equal to 1 to infinity modulus of zeta j raised to p is finite. If this series is finite associated with a sequence, then those collection of sequence belongs to the LP space. Here, the norm x where x is equal to sequence zeta j is summation j is equal to 1 to infinity modulus of zeta j raised to p the whole raised to 1 by p. This is the norm which we have defined in LP space. We have already discussed about the properties of LP space in general. And Q is the conjugate, meaning 1 by P plus 1 by Q should be equal to 1. So please remember these terminologies. So in order to prove that it's a dual, what need is we need a function which is actually an isomorphism from LP dash on to LQ. So before that, we need some elementary notions or elementary knowledge regarding the linear functionals which is defined on LP. For that, what we have done up until now is we have defined a basis on LP and represent every element x of LP in terms of the basis and then take an arbitrary linear functional defined on LP or which is in LP dash and operate on x and find the value of f of x, and associated with that we have defined the norm and we have defined the norm with respect to some relation, and using that we define some function from LP dash to LQ and prove that it satisfies all the conditions. This is what we are going to do. So the first thing which we need is we need an basis. Okay. So consider the shorter basis. A shorter basis of the space LP is denoted by sequence EK, where Ek is defined as summation which is equal to 1 when k is equal to j, which is equal to 0 if k not equal to j, or it is usually denoted as the Kronecker delta delta kj. So this is a sequence, Ek is a sequence in which the kth element is 1 and all the other elements are actually 0. That's the idea. So E1 is actually the sequence 1, 0, 0, etc. E2 is actually the sequence 0, 1, 0, etc. Ek is actually the sequence 0, 0, etc. 1, 0, 0, etc. So this is the sequences. Now, if we take an arbitrary element x which is equal to some sequence theta j which is in LP, x can be written as a linear combination of this. So x is actually sequence theta 1, theta 2, theta 3, etc., which can be written as x is equal to theta 1 E1 plus theta 2 E2 plus theta 3 E3 plus etc. So which is equal to summation j is equal to 1 to infinity theta j Ej. Which is clear from the definition of E1, E2, etc. You can easily define such. So we have taken a basis, and with respect to that basis, we have defined every element as a linear combination. Now take an arbitrary linear functional which is defined on LP. So let F is an element in LP dash, which means the dual space of LP. So clearly F is linear functional and is a bounded linear functional. F is linear, comma bounded. Then f of x should be equal to, by definition, f of summation j is equal to 1 to infinity theta j Ej, which should be equal to, by the property of linearity, summation j is equal to 1 to infinity theta j times f of Ej, which can be written as summation j is equal to 1 to infinity theta j times gamma j, where gamma j is equal to f of Ej. J varies from 1, 2, 3, etc. up to infinity. So we can write the value of f for any x element of LP as product summation j is equal to 1 to infinity theta j times gamma j, where gamma j is actually f of Ej. So this means actually every element, every linear functional is uniquely characterized by the images of the linear functional at the shorter basis elements. So this is what we have obtained. Now we have what we need is, as in the previous case of L infinity, in order to establish a function which is actually bijective from LP dash to LQ, what we are going to do is we establish that corresponding to every element in LQ, there exists a linear functional in LP dash, and corresponding to every linear function in LP dash, or which is defined on LP, there exists an element in LQ. So there should be a one-to-one correspondence between every element in LP dash onto every element of LQ. This is what we are going to establish first of all. Okay, which clearly establishes the one-to-one correspondence between the elements of LP dash and LQ. Okay, which is what we need in the further lines. So associated with this functional, we need an element in LQ. So take Q as the conjugate of key P, and this is true for every x. This result is true for every x, which we call equation number 1. And since this is true for every x, we can take a particular class of sequence. Let xn is equal to sequence theta jn. We define a sequence x1, x2, etc. And theta jn is defined as summation, gamma j modulus of gamma j raised to q by gamma j if j less than or equal to n and gamma j not equal to 0 and is equal to 0 if j greater than n and gamma j is equal to 0. I told you this is true for this result. Equation number 1 is true for every x. So in particular, this should be true for this xn as well. So xn, we have defined it as sequence theta jn, where theta jn is equal to summation j theta jn is equal to modulus of gamma j raised to q divided by gamma j up until the nth term. Okay. And gamma j is taken to be not equal to 0. And after the nth term, this is actually 0. Okay. So this means that up to the nth term, the first term of the sequence is modulus of gamma 1 the whole raised to q by gamma 1. Second is modulus of gamma 2 the whole raised to q divided by gamma 2, etc. So our sequence theta jn is actually modulus of gamma 1 raised to q divided by gamma 1, etc. up to the nth term, modulus of gamma n raised to q divided by gamma n and 0, 0, 0. This is our sequence. Okay. So we have chosen this sequence to have an element in LQ which associates with every linear functional f defined in LP dash. Now associated with this xn, the value of f of xn for any f belongs to LP dash is by definition which is equal to summation j is equal to 1 to infinity theta jn times gamma j. Now theta j is defined in terms of n. So up until the nth stage, which is the value is this, after the nth stage the value is 0. So we can define this sum as such. So summation j from 1 to n theta jn gamma j plus summation j from n plus 1 to infinity theta jn gamma j. So if you substitute the value of theta jn, we get summation j is equal to 1 to n modulus of gamma j the whole raised to q divided by gamma j times gamma j plus summation j is equal to n plus 1 to infinity. This is 0 times gamma j. So this is equal to 0 times any times is 0. Here gamma j is taken to be not equal to 0. So if we can cancel this, so this is actually summation j is equal to 1 to n modulus of gamma j the whole raised to q. So we call it as equation A. Now our objective was to associate every element of LP dash onto an element in LQ. So which is what we are going to do. Since f element of LP dash f of xn or modulus of f of xn should be less than or equal to norm f times norm xn, because f is a bounded linear function, because f is defined on LP dash. Now since xn is actually sequence theta jn, and which is taken to be an element in LP, norm of xn should be equal to summation j is equal to 1 to infinity modulus of theta jn the whole raised to p the whole raised to 1 by p. So this should be equal to norm f times summation j is equal to 1 to infinity modulus of theta jn the whole raised to p the whole raised to 1 by p. Now we have already defined in the case of theta jn. So theta j is already defined. So summation j is equal to 1 to infinity modulus of theta j n the whole raised to p can be written as summation j is equal to 1 to n modulus of theta jn the whole raised to p plus summation j is equal to n plus 1 to infinity modulus of theta jn the whole raised to p. Now after the nth stage theta jn is always 0. So this sum is actually 0. And before the nth stage, the value of theta jn is actually gamma j modulus of gamma j the whole raised to q divided by modulus of gamma j. So we substitute that summation j is equal to 1 to n modulus of this modulus of gamma j the whole raised to q divided by theta jn is modulus of gamma j the whole raised to q divided by gamma j. If we take the modulus, we get the denominator as modulus of gamma j the whole raised to p. Okay, the rest of the terms are 0, which we can write it as summation j is equal to 1 to n modulus of gamma j the whole raised to q minus 1, q divided by power 1 the whole raised to p. Now, since q is actually the conjugate, we have the result that 1 by p plus 1 by q is actually 1. So, 1 by p should be equal to 1 minus 1 by q, which on the right hand side, if you expand, q minus 1 by q is equal to 1 by p. So, which implies 1 by p is equal to q minus 1 by q, which implies if you move this q onto the left hand side and p onto the right hand side, q is equal to p times q minus 1. Now, if you look at this expansion, what we are going to get is here summation modulus of gamma j the whole raised to q minus 1 the whole raised to p. So this becomes summation gamma modulus of gamma j the whole raised to p times q minus 1. Now p times q minus 1 is actually q whenever p and q are actually conjugate. Here we have taken our q to be the conjugate. So this summation becomes summation j is equal to 1 to infinity modulus of theta jn the whole raised to p becomes summation j is equal to 1 to n modulus of gamma j the whole raised to q minus 1 times p, which is equal to summation j is equal to 1 to n modulus of gamma j the whole raised to q, since p times q minus 1 is q whenever p and q are conjugate. Now if we substitute on this expression modulus of f of xn, so f of xn modulus substituting in, if we call this as equation number 3 implies f of xn less than or equal to norm f times norm xn is actually summation j is equal to 1 to infinity modulus of theta jn the whole raised to p the whole raised to 1 by p. But we have already found the value of summation j is equal to 1 to infinity modulus of theta j and the whole raised to p, which is actually summation j is equal to 1 to n modulus of gamma j the whole raised to q. So this expression becomes summation j is equal to 1 to n modulus of gamma j the whole raised to q the whole raised to 1 by p. This is what we get. Now, we have already defined the value of f of xn, which is actually summation j is equal to 1 to n modulus of gamma j the whole raised to q. Since each of these quantities are positive, okay, then the sum is always positive. So sum is positive means if you take f of xn and modulus of f of xn, both of them are actually same because each of the terms are actually positive. So instead of modulus of f of xn, we can substitute the value of f of xn, which is equal to summation j is equal to 1 to n modulus of gamma j the whole raised to q. So from this expression, we have f of xn should be equal to modulus of f of xn because f of xn has all the terms positive. So f of xn is actually summation j is equal to 1 to n modulus of gamma j the whole raised to q, which we have already established. So if you substitute in this, so this expression becomes summation j is equal to 1 to n modulus of gamma j the whole raised to q less than or equal to norm f times summation j is equal to 1 to n modulus of gamma j raised to q the whole raised to 1 by p. So if you move this onto the left hand side, this becomes summation j is equal to 1 to n modulus of gamma j the whole raised to q divided by summation j is equal to 1 to n modulus of gamma j the whole raised to q the whole raised to 1 by p. Okay. So this whole power which is less than or equal to norm f. This whole power becomes q times 1 by p. So q by p. So this is actually some x raised to q divided by x raised to q by p. So if you write that, if you move on to the power onto the uh, upper side, so we are what we are going to get is, so here the power q is inside, the whole raised to 1 by p is outside. So this is actually the power q is inside. So we cannot actually combine them together. Sorry for that. And here this is actually x. If you take this as x, this is actually x raised to 1 by p. So the left hand side should be of the form x by x raised to 1 by p. So which is equal to x raised to 1 minus 1 by p. Okay. Now 1 by p plus 1 by q is actually 1. So if you move this onto the right hand side, so 1 by q should be equal to 1 minus 1 by p. So instead of 1 minus 1 by p, we can substitute the value of 1 by q. So this can be written as summation j is equal to 1 to n modulus of gamma j the whole raised to q the whole raised to 1 minus 1 by p. If you put x as this value, which is actually less than or equal to norm f. So which implies this is 1 minus 1 by p is actually 1 by q since q is the conjugate. So this can be written as summation j is equal to 1 to n modulus of gamma j the whole raised to p, sorry, the whole raised to q. Here it is not p, it is q. Q the whole raised to 1 by q is less than or equal to norm f. And we haven't fixed this n. So for any arbitrary n, this summation j is equal to 1 to n modulus of gamma j the whole raised to q the whole raised to 1 by q is actually less than or equal to norm f. Okay. So, which means that this summation j is equal to 1 to infinity, gamma j, the whole raised to q, the whole raised to 1 by q is also should be less than norm f. So, as n tends to infinity, we can write it as summation j is equal to 1 to infinity modulus of gamma j raised to q, the whole raised to 1 by q is less than or equal to norm f. Because this is true for any n. If you take this n as any particular value, this is true. So, this is true for any n means as n tends to infinity also, this inequality should be valid. So, this means that summation j is equal to 1 to infinity modulus of gamma j, the whole raised to q, should be less than a finite number. This norm f is actually a finite number because f is a bounded linear functional. So, which means summation j is equal to 1 to infinity modulus of gamma j, the whole raised to q, is actually a finite number, which by definition of LQ, meaning that the sequence gamma j, so which means that the sequence gamma j is an element in LQ. In order to become a sequence to be an element in LQ, the summation j is equal to 1 to infinity modulus of gamma j, the whole raised to q, should be less than a finite number. Here we have established that summation j is equal to 1 to infinity modulus of gamma j, the whole raised to q, the whole raised to 1 by q, is actually less than or equal to norm f. Okay, if you take the qth power on both sides, this means that this summation j is equal to 1 to infinity modulus of gamma j raised to q, is less than a finite number, which means that the sequence gamma j belongs to LQ. So what we have done is we have taken an arbitrary linear functional in f LP dash, and associated with that we have defined an element in LQ. So what we have done is corresponding to every f in LP dash, there exists an element sequence gamma j belongs to LQ, where sequence gamma j is defined as f of ej, where ej is the Schroeder basis of LP. We have done this. Now we have to do the reverse part as well. Now, conversely, corresponding to each sequence gamma j belongs to LQ, we can define a linear functional g which belongs to LP dash as g of x is equal to summation j is equal to 1 to infinity theta j times gamma j, where x is equal to sequence theta j, which is an element in LP. So this is, we have to prove that this is actually an element in LP dash. So two conditions must be satisfied. G should be linear and G should be bounded. So G is linear. If y is equal to sequence eta j is an element in LP and alpha is any constant, x is defined as this, g of alpha x plus y should be equal to, now the sequence alpha x plus y should be alpha theta 1 plus eta 1, alpha theta 2 plus eta 2, alpha theta 3 plus eta 3, etc. This should be the sequence. And this should be an element in LP because this sum, both of this sum should be bounded, then this sum should always be bounded as well. So this can be written as, by definition, this should be equal to summation j is equal to 1 to infinity alpha theta j plus eta j times gamma j. So which can be written as summation j is equal to 1 to infinity alpha theta j gamma j plus eta j gamma j. Now we can split up this alpha times summation j is equal to 1 to infinity theta j gamma j plus summation j is equal to 1 to infinity eta j gamma j. The first part is actually g of x, the second part is actually g of y. So this is alpha times g of x plus g of y. So clearly g is linear. Okay. Now we have to prove that g is bounded as well. So g is bounded. So g is bounded. For that, modulus of g of x should be equal to modulus of summation j is equal to 1 to infinity theta j times gamma j, which by Holder's inequality, if p and q are actually conjugates, this can be written as this is actually less than or equal to summation j is equal to 1 to infinity modulus of theta j raised to p the whole raised to 1 by p times summation j is equal to 1 to infinity modulus of gamma j the whole raised to q the whole raised to 1 by q. We can write as such, where sequence theta j is an element in LP. So by the definition of norm, if x is equal to this is actually norm x. So modulus of g of x should be less than or equal to norm x times summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. This is actually a finite number because we have taken gamma j to be an element in LQ. In order for that, summation j should to 1 to infinity modulus of gamma j raised to q should be a finite number. So which means that g satisfies modulus of g of x should be less than or equal to norm x times some constant c, which means that g is actually bounded. So g is linear and g is bounded, so which means g belongs to LP dash. So corresponding to every element in every C gamma j belongs to LP, there exists a g belongs to gamma j belongs to LQ, there exists a g belongs to LP dash as well. So this is true on both sides. So there should be a one-to-one correspondence between the element in LP dash and to the element in LQ. There's a one-to-one correspondence. So now we have enough tools to define an isomorphism from LP dash to LQ. So please recall equation A, which is defined as, we are going to recall this equation because we want to call it ascent tends to infinity, we want the value. So call it as equation B. Recall this equation. So we have equation B. From equation B, we have summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q is actually less than or equal to norm f. We have this. Now the thing which we need in order to establish this is the equality of the norms. So first part is here, we need to prove the second part as well. So let f be a linear functional, an arbitrary linear functional. We have f of x, modulus of f of x should be equal to summation j is equal to 1 to infinity theta j times gamma j, and this is actually by Holder's inequality less than or equal to summation j is equal to 1 to infinity modulus of theta j raised to p the whole raised to 1 by p times summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. Now this is actually norm x, where x is equal to theta j, which we have already defined. So modulus of f of x should be less than or equal to norm x times summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. Now if we move this on to the left hand side, what we are going to get is modulus of f of x by norm x is actually less than or equal to, so modulus of f of x by norm x is actually less than or equal to summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. So this quantity is actually an upper bound of this quantity for any x. Okay, so in the case of if we collect the modulus of f of x by norm x, this on the right hand side, this summation is actually an upper bound of this. Okay, so if we take the supremum over x element of LP x not equal to 0, modulus of f of x by norm x, it should always be less than or equal to summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q, because this is actually an upper bound. We have taken the supremum. Supremum is always less than upper bound. So on the left hand side, this is actually norm f. So norm f should be less than or equal to summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. So if we call this as equation C, from equation B and C, we can write norm f should be equal to, so from B and C, we can write norm f should be equal to summation j is equal to 1 to infinity modulus of gamma j raised to q the whole raised to 1 by q. Now we have all the tools to proceed with our isomorphism. So we can define an isomorphism from LP dash to LQ, which maps phi of f. The function is phi, which is equal to f of E1, f of E2, etc., which is equal to gamma 1, gamma 2, etc. And this is actually a bijection, because we have already proved that corresponding to every f element in LP dash, there exists a unique sequence gamma j belongs to LQ. So this is a one-to-one correspondence from LP dash on to LQ, and this is also linear, which also we have done or in the previous L infinity case. Okay, so you can take F1 and F2 element of LP dash and alpha be any constant. So phi of F1 plus F2. So the alpha F1 plus F2 should be equal to, if we substitute this value, which is alpha F1 plus F2 times E1 alpha F1 plus F2 times E2 and so on, which is clearly alpha times F1 of E1, F1 of E2, etc., plus F2 of E1, F2 of E2, etc. Okay, this is alpha times phi of F1 plus phi of F2. So this is alpha times phi of F1 plus phi of F2. So phi is actually linear and bijection, and which preserves norm as well, because norm of phi of f should be equal to norm of this gamma 1, gamma 2, etc., which is in LQ. In LQ, the norm is summation j is equal to 1 to infinity modulus of gamma j the whole raised to q the whole raised to 1 by q. And we have already defined that this is actually equal to norm f. So what we have done is we have established that norm of phi of f should be equal to should be equal to norm of F as well. So phi is a bijection, phi is linear, and phi preserves norm as well. So phi is an isomorphism. So phi is an isomorphism from LP dash onto LQ. So LP dash is actually isomorphic to LQ. So in other words, the dual of LP is actually LQ. So this is what we have done. We have established that the dual of LP is actually LQ. For that, let's just recall the steps. First, we have defined a shorter basis in LP as in the case of L infinity and wrote every element X in LP as the linear combination of the basis elements and take an arbitrary f in LP dash and find the value of f of x, which is actually a summation expression. And now the objective is to somehow relate the norm of x or y in LQ to norm of f. That's our objective. For that, we define a sequence and find the value of f of xn, and then f is bounded, which implies this inequality holds. Use the conjugate idea of p and q. Then we have established that norm f should be related with summation j is equal to 1 to infinity gamma j the whole raised to q the whole raised to 1 by p 1 by q by this relation, which implies that gamma j belongs to LQ. So we have established that corresponding to every element f in LP dash there exists a gamma j in LQ. Similarly, we will establish that corresponding to every element gamma j in LQ there exists a linear functional which is defined on LP using this sum. We proved that G is linear and G is bounded using Holder's inequality, and we have to have this equality of norms as well. For that, we use the Holder's inequality for an arbitrary linear functional and establish the equality. Norm f should be equal to summation j is equal to 1 to infinity modulus of gamma j the whole raised to q the whole raised to 1 by q. Now we have enough tools to define our isomorphism. We define an isomorphism from LP dash onto LQ by means of this map, which maps f1 to f of e1, f of e2, etc., or gamma 1, gamma 2, where e1, e2, etc., are the shorter basis of LP, and which is actually linear, which is actually bijection because associated with every element in LP dash there exists a unique gamma j in LQ. So there's a one-to-one correspondence which is a linear and which also preserves norm by our equation A and B. So we have established an isomorphism from LP dash onto LQ. So LP dash is isomorphic to LQ. So the dual of LP is actually LQ. This is an important example. Please try to understand it. Thank you.